The standard normal distribution curve. Yeah. Thank you. Yeah. I talk to him still. That's weird or not, but I do. All right, so let's go back to the standard normal distribution curve, which is normal, bell-shaped, symmetric, right? Is a normal type of curve. The special quality, the special thing about the standard normal distribution curve is that the mean of this curve is always equal to 0, and the standard deviation is always equal to 1. So it standardizes everything. That's why it's called the standard normal distribution, SND. So you'll see me label them SND. So whenever I do that, automatically you know that the mean is 0 and the standard deviation is 1. So the center of this curve is 0 because the center of a normally distributed curve is 0, the mean, and the mean here is 0. One standard deviation above the mean is positive 1. Two standard deviations above the mean is 2. And 3 standard deviations above the mean is positive 3. 1 standard deviation below the mean is negative 1. 2 standard deviations below the mean is negative 2. 3 standard deviations is negative 3. Obviously, I can continue because this curve continues in both directions, but we do focus a lot on that because the bulk of the area under the curve lies within 3 standard deviations of the mean. And then one particular thing that we also remember about a standard normal distribution curve are the values along the horizontal axis are z-scores. Because a z-score actually does tell you the number of standard deviations away from the mean a data value lies. So it corresponds to that. Now, that's just a little like recap of that. We're going to come back to this. I'm going to talk about a uniform distribution curve. And the reason that I'm going to talk about a uniform distribution curve is that there are two main properties that I want to show that I'm going to use later on in more difficult types of curves. The first property is that, so I'm going to, yeah. Sorry guys, okay. The first property is that the total area, I'm going to write total area under the curve is equal to 1. So because the total area under the curve is equal to 1, that means that there is a correspondence between the area under the curve and probability. Because total prob is probability, right? Total probability is equal to 1 or 100%. Total area is equal to 1. So there's a relationship. There's a correspondence between the area under the curve and the probability. So when you're finding area, so let's say you want to find probability, that's the same thing as finding area under the curve, okay? So you could be asked for percentage, find the area. You could be asked for the area, that find the probability. All of them mean the same thing. Now the first thing is, we're going to look at this example because it shows a uniform distribution. And it's a special type of distribution. It's a simplified type of distribution, but it allows me to show like this idea, this concept. And then I'm going to show it again in more difficult curves. So in this situation I have, during certain time periods at JFK Airport, passengers arriving at the security checkpoint have waiting times that are uniformly distributed. And the moment they say uniformly distributed, automatically you know, between 0 and 5 minutes, automatically you know that the probability of any outcome is equal to each other. So you have equal probability for uniform distribution. Okay? So let me write that real quick. Equal probability. So I'll show you what I mean in a second. Now, one more thing that I want to add that we're doing here is, prior to this lesson, we did discrete distributions, which was finite or countable. Find the probability of exactly, 2 out of 5 successes. Now we're doing continuous. Now we're doing continuous random variables, which means that the random variable could be a decimal, right? It could come from an infinite scale. So we're kind of moving into continuous type of variables. So the outcomes could potentially be decimals. They don't have to be finite or countable or discrete. But the first distribution that I want to talk about is called uniform, and this is a continuous type of distribution. Now, a uniform distribution, here's a nice visual of a uniform distribution, has two axes. The lower horizontal axis is going to be the minutes, right? Time in minutes, from 0 to 5, 0, 1, 2, 3, 4, 5, and everything in between. Everything in between. And then the vertical axis is going to be the probability of each, random variable outcome. So the thing is that because every outcome here has equal probability, if you think about it, right, total area under the curve has to be 1. And a uniform distribution, every single outcome that comes out of a uniform distribution has an equal probability. So if I draw this, it looks like a rectangle. Okay, these are the outcomes, and these are their corresponding probabilities. So I'm showing a continuous probability distribution, and it's graphed. Before we did tables, this is a graph because it's continuous. I can't list all the possible outcomes because I'm including everything in between these as well. Now I want you to remember that the total area under this curve is equal to 1. So I have to figure out, what this probability would be per outcome. Well, if the total area is 1, and if you look at uniform distribution, it shows a rectangular shape, the area under a curve is equal to the probability, and the area under the curve is equal to 1, and it's a rectangular shape, and I know base times height for a rectangle is area, and the base is equal to 5. I just don't know what the height is, but I do know that I want total area equal to 1. That allows the height, algebra, divide both sides by 5, to be 1/5 or 0.2. That means that the corresponding probability per any outcome is equal to 0.2. So I'm creating the probability distribution, which in this case is a graph version, a visual, a nice graph, because I can't, do tables in this case. It's continuous. I can't write all the possible outcomes. There's infinite outcomes because it's everything in between these as well. But because it's uniform, all the probabilities that come out or that correspond to these particular random variables are the same. So following the fact that, it's uniform, all these probabilities are equal, so it follows this rectangular shape, and the fact that the total area under the curve is 1, I can determine the probability per outcome. Sometimes you're given that and sometimes you're not. In this case, we were not, we had to determine. But it wasn't that hard because it's a rectangular shape and I know the area of a rectangle. So what could I ask you? What could you be asked? Given the uniform distribution illustrated, this is the illustration, find the probability that a randomly selected passenger, one randomly selected passenger, has a waiting time of at least 2 minutes. At least 2. So that means 2 or more. So again, I'm asked for probability, which means I want to find area. Right? I'm asked for probability. I want to find area. If I want to find probability, then I'm looking for area. So I'm looking for the area that corresponds to that. At least 2 minutes would be 2 or more. So that's this area of this curve. Okay, so I'm taking a piece of the rectangle now, but it's still a rectangle. It's a smaller rectangle. So I can still find it using, basic geometry. The probability that I have at least 2 minute wait is equal to the area under the curve, which is base times height. The base from 2 to 5 is 1, 2, 3, times the height of this rectangle, which is 0.2, which is equal to 0.6 or 60%. Okay, so this is what we call uniform distribution.